I thought I would do a video because not everybody was able to come to my office to test their PWM DAC. Some folks were doing a pretty good job on the ripple, and I discovered that a lot of times with the ripple it depended on where you were testing it, and that the board was even causing the ripple to increase. This is a technique where you get rid of the board to try to reduce the ripple as much as possible. It's a little impossible to tell that this circuit is a silent and key low pass filter. But let's go through a testing sequence that was required for this project. All right, so over here we've got in yellow V in, which is a square wave, and V out in green. And what I wanted you to be able to get from that is the fact that the mean is of the input 3.96 is very close to the output, which is 4. I'll tell you why I'm not using 1 volt peak to peak in a little bit. But the thing is that that's so close that the gain in dB is effectively 0 dB. And if we look at our Bode plot at 0 hertz, all right, even though in LT Spice you can't go to 0, you can get very close to it, but 0 hertz would be about 0 dB. But how can I get 0 hertz from a square wave? Well, in here it's flat and it's effectively DC because the signal has arrived to wherever it's going. So in this plot you can see that there's no ringing and that it looks pretty much like a critically damped circuit. And also notice that I'm taking an average. I've averaged it I've taken 71,000 measurements. So that mean is a pretty good indication of what we're at. We've gotten rid of a lot of noise. All right. Now let's go and just start increasing the frequency. All right. You see, after a while, the green doesn't go plus or minus 0 to 4 anymore. But notice that even though it's not rising as much, it's averaging out to the peak voltage divided by 2. Now we said we were going to operate this A to D at 200 kilohertz, so we're going to go to 200 kilohertz. And look at this. Just for looking at it at this scale, it looks like, yeah, our output is a DC signal. We've converted a PWM 200 kilohertz 50% duty cycle signal to a DC voltage. Now, of course, it only looks DC. We need to zoom in. To do that, I need to go to AC coupling, and then I can zoom in. We go to quick measure, statistics, and reset. Now, the mean of the green, the output, is 32 millivolts. Now you might be thinking, oh, hey professor, I got 11, I got 12 millivolts. Remember, my peak to peak is in fact 4 volts. So I would take that 32 millivolts and divide it by 4 to compare. The reason why I went to 4 volts peak to peak is so that I could try to make the output as big as possible due to scaling issues. All right, but 32, about 32 divided by 4 is about 8 millivolts, which is pretty good. Given that in simulation we were 6 to 7 millivolts. I'll try to explain why we're getting higher than the 7 millivolts from LT Spice in a bit. But this is your second plot, and from here you can calculate your effective number of bits and it will be, if you're getting what I got, you'd be getting more than 5 effective bits. All right. So now we want to go back and look at see if we can do a Bode plot. Now Bode plots, all right, you're supposed to measure everything at the same frequency, all right, and you measure at 1 hertz, 2 hertz, 5 hertz, 10 hertz, 20. You have to measure every single frequency in a Bode plot, all right, which is no problem for LT Spice, but doing it on a scope can take some time. So we've discovered, hey, I've got this point, almost 0 hertz, right? From looking at the DC part of a square wave. But the other important part is FC, and in this case, the minus 6 dB point. Because this is a second order filter, we can redefine the FC as minus 6 dB instead of minus 3. All right. Well, let's get 1 point, and this is at a kilohertz, and V out is very close to V in, so it's effectively 0 dB. Now what I want you to watch is me increase the frequency. All right. And at some point you will start to see this peak-to-peak measurement go down. Now the thing is on a 1 volt signal, the minus 6 dB point is about 0.5. So I've multiplied that by 4, and so I should see the V out go down to about 2. All right, so that's, roughly, let me just get a little more. I'll just leave it here, okay? So right now I'm reading, and let's just reset our statistics. Okay. I'm measuring 12.3 kilohertz. I'm getting at about minus 6 dB. All right, so that's this point here, right? Except instead of what our calculations showed, that it should be around 15 kilohertz, Spice gave it at about, sorry about that, 14 kilohertz, but I'm actually measuring about, can you read that? 12 kilohertz. All right. Now, why is that? And what the first reason is that when I said that the Salon and Key was a second order circuit, it's not exactly true. Inside there's a capacitor that is used to stabilize the output, and so if you take a Bode plot, that's the frequency response of the op amp. And so at this point around 15 kilohertz, the gain is about minus 32. So 10, the gain is 32. 32. So this will give me the input, or that'll give me the gain of the op amp at about 15 kilohertz, which it's about 40. The open loop gain at 15 kilohertz is about 40. Well, if we look at the Salon and Key and just say, hey, there is, whoops, my bad. There is a buffer going on here, and the open loop gain, the gain of a buffer equals V out over V in times the open loop gain plus 1. And when the open loop gain is shrunk down to 40, all right, 40 divided by 41 is actually starting to reduce the output to a measurable amount. Now, it's a lot more complex than that. It's a little bit beyond the first circuits course, but just know that we're getting close to where the open loop gain being infinite is not a good approximation. Still, what else is going on? Because when I calculate that out, it still is kind of a small effect. Well, one thing I noticed is, we'll take another person's circuit, is that depending on where you measured or put your ground, right, and in this particular example, this is ground. So if you measured close to the circuit, you got different results if you put your ground far away from that capacitor. And you could change what results you got. Also, people who had a lot of loops and a lot of wires and things all spread out, they had an increased ripple as well. That can be explained if we flip this over, in that, yeah, we have metal. The metal has resistance, but metal that is next to each other is effectively a capacitor. Even a metal wire has inductance. Fortunately, I've got something called the impedance analyzer. And what I did is solder in two wires. And in this configuration, I'm measuring the capacitance between two lines. And notice this, all right? I'm getting a capacitance, but it's starting to act like a capacitance. Remember, capacitance, the impedance is 1 over S. C, but it's starting to act like a capacitor that you can measure at 90 kilohertz, when our frequency of our pulse width modulation is 200 kilohertz. All right, so there's capacitors even in this board that we're not fully taken into account. And then let's look at the inductance. Okay, now if you can see, I'm going in, I'm measuring the same line. I just press start, and now you should see an inductor response. I'm going to just increase the speed of that. Okay. Now, yeah, it doesn't really start to behave like an inductor until about 640 kilohertz. But the thing is even though our FC is at 15 kilohertz, I'm going to show you now why those higher frequencies matter. This is something called the Fourier transform of a square wave, and if you've read the TI data sheet, we're trying to get this AO and filter out all of this high frequency. But this series, if taken to infinity, will make a square wave. All right. This is the part we want, which is the voltage times the duty cycle, right? And we want to filter out all of these constants. But the thing is notice, even if you calculate these out, these coefficients get smaller, smaller, smaller. But notice, we sum them to infinity. When we look at the Salin and Key filter, this doesn't keep going down to zero, closer and closer to zero. It kind of bottoms out. That's because the op amp stops working like an op amp. You can't assume these two things are equal, and the capacitor just acts like a short. So we will get these high frequency components due to the fact that it's a square wave. And these high frequency components show up on the board here at about 600 kilohertz. And for the capacitor that we saw before, it shows up even at, 60, 80 kilohertz. So it's no wonder that our FC is a little bit lower than what we expect. Also, I do believe for this batch of op amps, this whole line is pushed down by some amount. And the gain bandwidth, which is where this goes to zero, does vary statistically from batch to batch. So really, why is FC off? The op amp is a little bit slower than the spec. Why is it even in simulation not matching results exactly to our hand calculations? Because the open loop gain isn't infinite around 15 kilohertz. What else is going on is that we have all this high frequency content that is being picked up by the parasitic resistors, inductors, and capacitors of our board.